Hello, good morning. Here we are with the problem of Gauss when he was age of 8. So he showed with a heuristic method that the sum of the first 100 numbers is 5050, and then generalizing the same method of Gauss, we found a general formula for the sum of the first n natural numbers. The sum is n plus 1 times n half. So we concluded the last videos by stating that these formulas are found by heuristic method, so we just found them without proving them, and the rigorous way of proving them is used the principle of induction. So I will show you how to use it for this problem. And so the starting point is that we aim at proving that the sum of the first n numbers, 1 plus 2 plus n, is equal to n plus 1 over 2 for every natural number n. So just a notation, we will use it a lot. This can be written as the sum for j starting from 1 and going up to n of j. Okay, this is just a way of writing down this formula. Okay, sigma is the symbol of the sum, j is an index, and so we let j going from 1 to n, and the terms we sum are exactly j. So when j is equal to 1, this is 1. When j is equal to 2, this is 2, up to n. When j is equal to n, this will be n. Okay, good. So how to prove it by using the induction? We use two steps reflecting the fact that here, remember, this must be true for p equal to 0, and this must be true for for n plus 1, provided that it is true for n. Let us do it. So the first step, this is the so-called induction basis. N equal to 0. Sometimes one starts from n equal to 1, because here the sum of the first 0 numbers, it is not so meaningful. However, we have that 0 times 0 plus 1 divided by 2, this is equal to 0. And it is acceptable that the sum of the first 0 numbers is 0. Okay, but this is true, this is perfectly convincing. But if you are not convinced, because talking of the sum of 0 numbers is somewhat ridiculous. However, it is true. But if you are not convinced, consider n equal to 1, and then you have 1 times 2 divided by 2. This is equal to 1. So the sum of the first one number is 1, because the only number you have to sum is 1. Okay? And this is called the induction basis. It is just a word. Sometimes when speaking it is useful to know the words. The second step is the so-called induction step. So you assume that the formula holds for n, and given this assumption, then you prove that it holds for n plus 1. So you start with the sum of the first n plus 1 numbers, 1 plus 2 plus 3, you go up to n, and then you have n plus 1. Okay? Now, since you assume that the formula holds for the first n numbers, here you write n times n plus 1 over 2. Okay? And then you have to add n plus 1 here, plus n plus 1. Now you collect out this n plus 1 terms, and you end up with n over 2 plus 1. The n over 2 term comes from here, n over 2 times n plus 1, and the 1 comes from here. When you collect out this n plus 1, you end up with a 1 here. Okay? So develop the computation, and you have n plus 1, n plus 2 over 2. This seems to be quite strange, but indeed it is correct. Why? Because this is n plus 1 times n plus 1 plus 1 over 2, and this is the formula we are looking for, because you are looking for the formula of the sum of the first n number when instead of n we consider n plus 1. So instead of n, it is correct that we have n plus 1, and instead of n here we have n plus 1 again. So it is correct, because this is the formula n plus 1 over 2 when n is replaced by n plus 1. Good. And now I give you as an exercise to compute the sum of the first n squared. Or better, not to compute, I don't try to find some heuristic. It is not so easy like before, but you can try to find it. Prove that the sum of the first n squared number is n times n plus 1 divided by 2n plus 1 divided by 6. Okay, and again you have to do it by induction. So first prove it for n equal to 0, and this is easy, and then assume that it holds for n equal to n, and prove it for n equal to n plus 1, okay? Like we did for the other formula. Okay, and this is all for what concerns the naturals, okay? And now remember that the naturals for natural numbers, the internal operations we defined are sum and product. So for instance, there is no subtraction. What does it mean? It means that there is no inverse. So there are no inverses for the sum, for the operation of sum. Namely, what I am doing, what I am saying, that given n in n, there is no m in n such that n plus m is equal to the neutral element for the sum, which is 0. Of course, the only case in which there is this inverse is the trivial case, n equal to 0. In that case, also m is equal to 0. Okay, but in general, there is no inverse. In general means that there are some numbers for which it does not exist. So we extend, this is the important step, we extend the set of naturals by introducing the inverses with respect to the sum for every natural number. So let me explain a bit better what I mean. So you have 0 here, we have 1, we have 2, we have 3. These are the naturals, but now here you write down -1, -2, -3. So in such a way that the inverse of 1 is here, is -1, the inverse of 2 is here, is -2, and so on and so on. Good. And the set we obtain here is Z. So we obtain the set of the integers which is Z. Everybody knows this is given by 0, plus -1, plus -2, plus -3, and so on and so on. And again, there are two operations, sum and product, which are again commutative, associative, and distributive one with respect to the others. They have neutral elements which are again 0 for the sum and 1 for the product. And then there are inverses with respect to the sum. Every n has a -n, and there are no inverses with respect to the product, except for the case of the number 1. And probably you already understood what is the next step. There are two steps indeed. The first step is to include, to add the inverses with respect to the product. First. Second, close the set you obtained with respect to the product. So this step is a bit more complicated than the one before, because in the step before, when you include the inverses with respect to the sum, then the set you obtain, which is z, is closed with respect to the sum. You sum two integers like that and you obtain an integer. Here, the situation is quite different. One, first, for every n, which is integer numbers, but which is not 0, for 0 it is not possible to do that, you introduce the symbol n to the minus 1 or 1 over n, which is the inverse of n with respect to the product. It means that n to the minus 1 times n is equal to n times n to the minus 1, which is equal to 1. Okay? But now we notice that the set we obtain is not closed. With respect to the product, since if you consider two n and m different and both non-zero, and you consider n to the minus 1 times m, this in general means that in particular case may be, but in general it is not an integer. For example, n equal to 2, m equal to 3, you have that 2 minus 1 times 3 is not an integer, is 3 over 2. It's not an integer, nor an inverse of an integer. Therefore, the step 2 consists in including all this number like 3 over 2. All symbols, all quantities, let me call them numbers, of the type n minus 1 m. As a result, we obtain the set named by Q which is the set of rationals and which is of the form P over Q, P in Z, Q in N minus 0, and let me say absolute value of P. We will define the absolute value later, but you know what it is, the absolute value. The absolute value of a number is the same number if the number is positive, and it is the same number with a minus sign if the number is negative. Okay? P and Q have no common divisors. This is Q. And so what are the elements of Q? Then okay, it can be useful here to write down a table, and a table like that, there are many ways to introduce a list of rational numbers, but let me do it in this very easy way. So we start here from 1. Of course, here there is 0, and then 1. Here we put minus 1, and here 1/2 and 2, and here minus 1/2 minus 2. What I am doing, I am doing this in this line. In the first line, I'm including the numbers in which P and Q are both less or equal than 1. Here, both less or equal than 2. And so I go farther and farther. So I have 1/3, 2/3. 3/3 cannot be there because it is equal to 1. So I have 3/2 and 3 for P and Q both less or equal than 3, and here I have minus 1/3, minus 2/3, minus 3/2, minus 3. Okay? And so on and so on. Again, I can do 1/4, and then 2/4, it is not there because it is equal to 1/2, so we have 3/4, so 4/3 and 4. And again, the negative, minus 1/4, minus 3/4, minus 4/3, minus 4. And here I put just all numbers where P and Q, numerator and denominator, are both less than 4, and so on. In this way, you can construct a list of rational numbers. Rational numbers are these ones, are the fractions. Okay? Okay. Which are the operations of Q? Are the usual ones, but they are more complete now. You have again sum, product, which are commutative, associative, and distributive. And okay, both have neutral elements, 0 and 1 again. And for every element of Q, there is the inverse in Q with respect to sum, and the inverse, which is another one, with respect to product, except for the 0. 0 has no inverse with respect to the product. And okay, the other thing we can introduce is the representation, is the standard representation. So it is well known that every number z equal to p over q, rational number, can be represented in the following way. P over q is equal to a certain n, which is an integer, and then there is a dot, beta 1, beta 2, beta k, and so on and so on. Okay? N is a natural number, or better, an integer, and it is not really the integer part, okay? And it is an integer, and every bj, b with every index, is a number between 0, 1, up to 9. Okay, this is the string after the point is very important. This is the standard representation. And about this representation that you know very well, and it is what you use every day. And the first point is that every representation of a rational number is eventually periodic. This may seem to be strange, but it is not the case, because, for instance, if you have the number 2, which is rational, of course, 2 is equal to 2.0000, so 0 is periodic. The second point, if you compute p over q and you do the division in the technique you learned at elementary school, at some point you find that beta 1, beta 2, and so on, at some point they start repeating a certain period. I don't know, beta j up to beta j plus k, and then again beta j plus k, and so on and so on. It's periodic like that. Second, vice versa, every representation which is eventually periodic denotes a rational number. And you know from elementary school there are techniques in order to pass from the fraction from the representation to the fraction, and vice versa. And the last one is the most delicate. It is not true that the representation denotes uniquely the rational number. So there are rational numbers that admit more than one representation. Indeed, they admit two. For instance, the number 1. The number 1 is 1.000, but is also equal exactly equal to 0.9999 and so on and so on. This is a surprise in a priori, but it is very easy to prove, because if you consider the fraction 1/3, it is 0.3333, everybody knows. Then multiply it both sides by 3. And here you have 1 is equal to 0.999, and so on and so on. Very easy, very stupid. And in general, the number n dot beta 1 beta k all zeros is equal to n dot beta 1, and here we have beta k minus 1, and then all nines. This is a sort of pathology of this representation, but it is very easy to overcome, because we just say that by convention we will always use the development with all zeros. Okay, this is almost all for natural numbers, but there is a problem with natural numbers that forces us to look for another set of numbers, to enlarge again and to obtain the real number that will be our environment. Okay? Here I stop and I go to the next video.